Taking a look at acid-base indicators here. You'll need your periodic table because there's a list of acid-base indicators and their colors on the back side. So what do the different colors of thymol blue indicate? Well, on the back of our periodic table, it lists two different ranges for thymol blue. We have 1.2 to 2.8, and that is red to yellow. It also says 8.0 to 9.6, which is yellow to blue. Not all indicators have two ranges listed. Most of them are just one, but thymol blue includes two, and I think it's a good example here. So I always look at these on a number line. So thymol blue has 4 points on a number line that are important. It's 1.2, 2.8, 8.0, and 9.6. 1.2 to 2.8. This says it's going from red to yellow within this range. Therefore, at 1.2, it's red. Anything less than 1.2 is also red. So I'm going to color that in on my number line. 1.2 and less is red. Now it says that yellow, 1.2 to 2.8 is red to yellow. So at 2.8, it will turn yellow. Now, I would hope that it's yellow until 8, so let's just double check here. At 8, it says it's yellow again. Therefore, yellow to blue from 8 to 9.6, anything less than or equal to 8 is yellow. So it's between this range is what that's describing of pH values that will be a yellow solution. So if I have a neutral solution, pH of 7, and I drop in a few drops of thymol blue, it will turn yellow, and it will indicate that it is somewhere within this range of values. Now, greater than 9.6 is blue. So 9.6, from 8 to 9.6, it's transitioning from yellow to blue. At 9.6, it will be blue, and it'll be blue anywhere beyond 9.6. So if I have a pH of 13 and I add some drops of thymol blue, it will stay blue. Now, what is it in between? Well, let's think about it. Let's go from 8 to 9.6. If I'm transitioning from yellow to blue, think about your rainbow. What color do these two mix together to be? Green. So if I have a solution that turns green, I know that the pH is between 8 and 9.6 after I've added that thymol blue and it's turned green. What is the color between 1.2 and 2.8? Well, red and yellow mixed together makes orange. So if I add thymol blue to a solution and it turns orange, I know that the pH must be between 1.2 and 2.8. So thymol blue has 5 different colors to indicate the pH of the solution. If I see any of these colors, I can estimate the range that the pH is for that solution. So an acid-base indicator is a substance that changes color when the pH of a solution changes. Indicators exist in 2 forms that each have a different color. They also have very complicated molecular structures and formulas. So abbreviations are used to identify the color, the indicator, sorry. So for instance, what we're looking at here is phenolphthalein. So phenolphthalein has this giant structure. And when it turns pink, it still has a giant structure. It's just different number of H's. So we use these abbreviations, if you will. So on our periodic table, we can actually see them. HIN, where IN can be changed with any other abbreviation for each indicator, represents the lower pH form of the indicator, or the more acidic form. IN minus, so its abbreviation negative, is the higher pH form for an indicator. It's the more basic version. So each indicator has a pH range that is unique to that particular substance. Again, we're going to look at the back of the periodic table. The abbreviation for methyl orange is MO. The pH range represented by methyl orange is 3.2 to 4.4. When it is its lower pH value, what color is it? Let's say that this is color is what we're describing in these. Its lower version, when it is HMO, will be red. When it is MO minus, the higher pH value, it will be yellow. Filling out the rest of the table like that, go ahead and pause it and fill in your table. So I've written in the rest of these here, maybe pause it and double check your work. When we use acid-base indicators, well, we use them in titrations, which we talk about at the end of this unit, and to estimate the pH of a solution. So it'll replace the work of a pH meter. It's just not as accurate. It doesn't give us one exact reading. It will give us a range. So predict the indicator color for the specified pH. So if I have a solution of 2.8, what color will bromocresol green be? Well, looking at our periodic table, bromocresol green is a pH range of 3.8 to 5.4, which turns yellow to blue. Because 2.8 is less than 3.4, it will be a yellow solution. Phenol red has a transition of 6.6 to 8, which is yellow to red. If it is 8.5, it's greater than our 8, therefore phenol red is red. Cresol red has two pH ranges that we need to look at. If cresol red is 8, a pH range of 8, it's beyond the 0 to 1 pH range. It's within the 7 to 8.8. 8 lies between these two values. Therefore, it's in the middle of transitioning from yellow to red at this point. When it is transitioning from yellow to red, cresol red at 8 will be orange. If we have a pH of 1.6, cresol red, we're looking at the first pH range of 0 to 1. It is greater than 1, but it's still less than that next range of 7. Therefore, it will be yellow. Methyl violet with a pH of 1. Methyl violet transitions from 0 to 1.6 from yellow to blue. 1 falls between that range, therefore it's in the middle of the transition from yellow to blue, and it will be green. Our next example here says one solution was tested with several different indicators to determine the pH. So we took small samples of it, put it maybe into a well plate, and added a drop of each of these indicators to different wells, not all to the same solution. The following results were obtained, and what is the pH of the solution? So orange 4 turned yellow, bromocresol green in this solution was blue, phenol red was yellow, bromothymol blue was yellow. We can use these four indicator ranges to decide on a general range of pH that this solution could be. So looking at our periodic table, orange 4 has a range of 1.4 to 2.8 when it goes from red to yellow. So if our solution is yellow, it means that the pH must be greater than or equal to 2.8. Bromocresol green is blue. Well, 3.8 to 5.4 is its range, and yellow to blue is the color. Therefore, if bromocresol green is blue, it must be greater than or equal to 5.4. This is pH every time. Phenol red is yellow. Phenol red is yellow when the pH is less than 6.6. Less than or equal to 6.6. And bromothymol blue is yellow when the pH is less than or equal to 6. Now, some of you can look at this and tell exactly what the pH range is. However, I would urge you to try and use a number line to describe this. Our number line has 4 important numbers on it: 2.8, 5.4, 6, and 6.6. Obviously not drawn to scale. So what we're going to do is we're going to use our number line to color it in for each pH. So when orange 4 is yellow, the pH, it says, is greater than 2.8. So our pH must be somewhere on the pH range greater than 2.8. Bromocresol green, being blue, means that it is greater than or equal to 5.4. So our pH now can't be less than 2.8. It would have given us orange 4 to be yellow, but bromocresol green would not have been blue at that range. So our pH in general must be greater than 5.4 right now. When phenol red is yellow, the pH was less than 6.6. At this point, if our pH was greater than 6.6, let's say it was 8, Orange 4 and bromocressyl green would have the correct color, but phenol red would not be yellow. Our last one, bromothymol blue being yellow, means a pH of less than 6. So what this tells us is that the pH range for all 4 of these to be true needs to be between 5.4 and 6. So the pH is less than or equal to 6 and greater than or equal to 5.4. When you write a pH statement, it must be one inequality. You don't want to write 2 separate ones here. All right, our last example. A solution is tested with multiple indicators and the colors are noted. Phenolphthalein turns colorless, thymol blue is yellow, methyl red is orange, and bromocressyl green is green. So what I did is I made a list of the colors. So we have that phenolphthalein was colorless, thymol blue was yellow, methyl red was orange, and bromocressyl green is green. When phenolphthalein is colorless, it means that the pH is less than or equal to 8.2. When thymol blue is yellow, it means that the pH was between 2.8 and 8. When methyl red is orange, it means that the pH was between 4.8 and 6.0. And the last one, when bromocressyl green is green, the pH is between 3.8 and 5.4. We're still going to draw a number line. Okay, this time we just have more values to put on it. So we have 2.8, 3.8, 4.8, 5.4, 6, 8, and 8.2 if you go in numerical order. Again, definitely not drawn to scale, but that doesn't matter. So phenolphthalein is colorless when it was less than 8.2. Thymol blue was between a pH range of 2.8 and 8. Methyl red was between a range of 4.8 and 6. And bromocressyl green is between a range of 3.8 and 5.4. Where are all of these true or overlapped? Between 4.8 and 5.4. So the pH is less than or equal to 5.4 and greater than or equal to 4.8. That was A. What is the hydronium ion concentration range of this solution? So this is going to incorporate some of our pH work. So what we can do is we can calculate the pH for each of our values in the pH range here. So concentration of H3O plus is equal to 10 to the negative pH, which is 10 to the negative 4.8. There's one decimal place, therefore I get one significant digit. So 2 times 10 to the negative 5 moles per liter. Over here, we get the concentration of H3O plus is equal to 10 to the negative 5.4, which is one significant digit. And I got 4 times 10 to the negative 6 moles per liter. Now notice, this is a higher pH value and a lower concentration of H3O. Remember, the lower the pH, the higher the concentration of H3O plus. So that was B. And C, would a hydronium ion concentration of 3.8 times 10 to the negative 5 produce these results? What I did is I made a little number line with our concentration and pH. So our concentration of H3O, the smaller one, is 4 times 10 to the negative 6 moles per liter. And our larger one is 2 times 10 to the negative 5 moles per liter. Now, where does this value fit? So 3.98 times 10 to the negative 5 is a bigger number than our 2 times 10 to the negative 5. So it is off the scale. Oopsie. So it doesn't fall within the range here that would describe this situation. Therefore, it does not produce the above results. Another way we could do this is just change our concentration into a pH value. So pH is the negative log for your H3O plus concentration. So negative log 3.98 times 10 to the negative 5 moles per liter. And we get that it would be 4.400 as a pH, and that would be below the range here. And again, it would not produce the same results. So either or, you can convert this, put it on our scale, or convert it into pH and look at our original scale to recognize that it won't work. Your homework is a worksheet online today, so take a look at that there.